I'm sure.
All good? Yeah. Oh, yeah. Yeah, sure.
Hi, everyone. Yeah, thanks for coming after lunch. So I just want to make a couple of quick announcements before we start with our afternoon talks. We're going to have a town hall on Monday at 1 p.m. Just on the second floor. So if you're, we'll just talk about like what our plans will be kind of for the rest of the semester going forward. So if you want to come to the second floor at 1 p.m. and we'll all kind of introduce ourselves and stuff. And we'll also have, I'll send this in an email later today, but next week we're going to have a seminar on Tuesday by Amy Ward, and then Wednesday we're going to have like a longer whiteboard talk by Z. Okay, so that's it for the announcements. And so I'm very happy to introduce Michael Kim, who is a postdoc here currently at Berkeley, and he's going to tell us a very exciting area on multi-calibration. So thank you, and take it away.
Thanks,
I will write it in my email. It'll be just around here. Yeah.
Great. So thanks for the intro. I am Michael Kim. I'm a postdoc here at the Miller Institute, and I hang out at Simon's a bunch. So I'll be around all semester. So please say hi. I'm happy to chat about stuff. So today I'm going to tell you about some research that I've been involved in on this topic of multi-calibration and its role and sort of how it's implicated in thinking about fair decision making. Okay, this talk overviews a bunch of research with a bunch of different people. It's really meant as a tutorial. I really expect no prior knowledge, but for that reason, please interrupt me, ask me questions. I have way too many slides and I don't expect to get through, all of them at all. So yeah, interrupt me. I'd much rather have things be clear for everybody to get something out of it than to get through all of my slides. Okay, good. So let's get started. So I don't need to tell this crowd, but algorithms are everywhere we look these days, right? And more, they're not just computers for us. They're not just calculators, but they're implicated in consequential decisions, often about people, right? So they're driving our cars. They're running sophisticated targeted advertising platforms. They're making medical decisions for us. And actually, I like all of these examples because in each of them, historically, the human decision makers have been highly regulated, right? So if you want to drive a car or if you want to practice medicine in this country, you need to go out and get a license. And often this license takes you a long time to get. If you want to be an advertiser in this country, well, there are tons of federal laws with strong consequences protecting individuals from discrimination in advertising, say for housing and jobs, things like this. So as we move a lot of our decision-making processes from a human decision maker, who we've historically regulated very highly, to algorithmic processes, we need to start building up a language to be able to reason about whether these algorithms are fair or not, and whether how we should regulate them, how we should understand whether the decisions they're making or implying are fair. Okay, so that's sort of the high-level basis of this research investigation. I want to start with just a cartoon example of the type of discrimination or unfairness that I'm going to be focused in this talk. In particular, I'm going to focus on an issue that I call miscalibration and how it can lead to unfair discrimination. So we're going to be talking about risk prediction. A concrete example you might have in mind is predicting the risk of, say, kidney failure in a medical context. Okay, and so in this cartoon, I'm going to plot on the y-axis the predicted risk score and look at how this predicted risk score varies as a function of the true underlying risk. Okay, And so to start, I'm not gonna introduce definitions yet. We'll get to that later. But intuitively, we say that a predictor is calibrated if, on average, the predicted risk score tracks the true underlying risk. Okay, so indeed, we can see in this cartoon that on average, at least, it seems as though as we move the actual risk upwards, so too does the predicted risk score move. So that seems pretty good. But maybe when we look at these predictions a little bit further, upon further inspection, we find some attribute that we can split up and partition the population on this attribute and discover two different populations, this orange and this blue population. And at least intuitively, it seems as though these predictions are no longer calibrated to one another. That a prediction in the orange population means something different than it does in the blue population. Okay, and this phenomenon of miscalibration has been widely observed. In particular, it was very strongly demonstrated, for instance, in the context of medical renal failure predictors. In this paper in Science a few years back, showing that standard medical risk predictors that are out there being used in hospitals are miscalibrated according to or across groups defined by race. Okay, so in particular, in this cartoon, the white patients might be represented in this yellow line, whereas Black patients would be represented in the blue line. What's the consequence of this miscalibration? Well, when medical professionals use a fixed threshold on the predicted risk score to determine who qualifies for advanced care, right? Who is really the sickest patients? Even though they're using a fixed threshold on the predicted risk, in effect, they're using two different group-specific, race-dependent thresholds on the true risk. And in order to qualify for advanced care as a Black patient, you need to be considerably sicker than your white counterpart patients. Okay, so the result is disparate treatment on the basis of race. That for the same level of sickness, Black patients are overlooked in these hospitals that are using these algorithmic predictors compared to their white counterparts. Question?
Here, it seems like an easy problem to fix by shifting. Isn't it like, would it be more difficult if it's certain type of a much higher variance, like uncertainty in the prediction? Here it seems like it's just a shift.
Yes, in this cartoon example, I'm drawing it as plainly as possible. But in fact, when you look at these empirical plots of the risk curves, they were like remarkably miscalibrated in a very obvious manner. And so sometimes it's as easy as asking the question, are you calibrated across these attributes? We'll talk about some of the challenges in that simple of an auditing process. Great. Any other questions about this cartoon example?
I don't know if you're going to define what is exactly.
Yeah, so I probably won't define it exactly, but you can imagine that it's just predicting the probability of an event. Say predicting the probability of renal failure in this case.
You don't actually know the actual risk that you're saying.
Yeah, that's exactly right. So how do you generate this curve in the real world? That's a pretty sophisticated challenge, and why this was a science paper. But I think it takes a lot of work. But yeah, this is a cartoon. You can imagine that there actually is a true risk. Yeah.
I'm confused by the nomenclature. I understand that you're getting different treatments, but why is this called miscalibration if the two curves seem like pretty good description of your data?
Let's wait till I actually define what calibration is. Yep.
But these are the true curves with the true data, or no?
I mean, I have an actual risk here, and I have a predicted risk score. So I'm saying that the predicted risk scores mean different things in these two populations.
Got it. I misunderstood.
Yep. Great. So this is meant as a cartoon, but meant to represent something that really happens out there, and is sort of an example of a phenomenon that I think a lot of us are hearing more and more about, where algorithmic predictions are implicated or facilitating even unfair decisions that we see and hear about in the real world. So what, as theoretical computer scientists, should we do about this? Well, rather than trying to pick apart and look at every single example that we see and come up with a solution for that example, we're going to try to take a more foundational approach, okay? Where we try to identify general patterns of unfair behavior that arise as a consequence of algorithmic predictions, and try to formalize these examples into definitions of fairness in the language of theoretical computer science, math, and statistics. Okay, and really the focus of this work, a huge focus of the work, is trying to make sure that we have the right definitions. Definitions that balance the need for general purpose solutions, as well as an awareness for the context in which the notions are going to be deployed. And ideally, these definitions will help us to really clarify what we can and cannot expect from machine learned predictions, and really facilitate open debate about these hairy notions of fairness and discrimination and how we should make progress towards fairer decisions. Okay, the sort of pie in the sky eventual goal that I would love to achieve is some sort of provable certificate of fairness. That when you're using a predictor in the wild, that you could look and the predictor would provide you with some certificate saying, hey, this is a proof that my predictor satisfies some notion of fairness, in the same way that your modern browser provides you with some certificate that everything has been implemented correctly and on the basis of cryptography. Right, so really we're drawing from this tradition of abstracting a problem and coming up with definitions to achieve things like security, privacy, and fairness. Okay, so in this tutorial, I've already alluded to, but I'm going to start by talking about fairness and prediction tasks. Okay, and that will be where we spend most of our time. But then I'm going to switch gears and talk about something that seems unrelated, which is optimal decision making in the context and through the lens of loss minimization. Okay, and then yet further away from this, I'm going to talk about pseudorandomness. I'm going to talk about pseudorandomness in the context of learning. And at this moment, I expect many of you are saying, like, what the heck? How are all of these connected? In fact, we're going to see that there's a central notion called multi-calibration that connects all of these perspectives, that has had, started in this literature on fairness and prediction, but can be interpreted and says something about all of these topics. Okay, so that's sort of the highest level roadmap for the day. And I'll pause here to catch my breath and ask if there are any other questions, and then we'll get started on fairness and prediction. Any questions? Okay, great. So I'll give you some definitions. And so first, let's just get our setup straight. We're going to be working in a supervised learning model where we think about the inputs X as representing people or individuals. Say, X could be a patient's medical features and their history. And we'll think about trying to predict an outcome Y. For the sake of this talk, let's assume that outcomes are binary. So for instance, an indicator of whether this person had renal failure in the next week. Okay, and we're going to be working in sort of an agnostic pack model, which just means that we assume that there's some fixed but unknown distribution over the individual outcome pairs, X, Y. Okay, in particular, we're making no assumption about the relationship between X and Y. The mapping from X to Y could be arbitrarily complex. Okay, hopefully this is standard for many people in the audience. So the guiding principle that we're going to work with is to try to imagine that we're going to try to learn the individual probabilities of an outcome Y, given a patient's information, given the features X, and we're going to try to do this across the population as a whole, ideally to enable accurate and fair decisions. To do this, we're going to make a few assumptions. One is statistical, one is computational. The statistical assumption is that I'm going to assume that I have access to data that is unbiased and representative. Unbiased meaning that the outcomes that I'm observing are actually the outcomes that I want to predict, okay? So that reliably, I can trust that when an example is 1, it's giving me positive signal towards renal failure, say. And when I see a 0, that it's giving me a reliable signal that this person is unlikely to suffer renal failure. And representative meaning that I'm seeing examples from people across the population as a whole. That I want to learn about these different subpopulations, I need to be able to see them in my data. Okay, and computationally, I'm going to make, just sort of assume that I have access to supervised learning primitives. Say, very similar to the types of assumptions that I would need to run algorithms like boosting. Okay, good.
Distribution from which the population is drawn.
So agnostic here is referring to the fact that I'm not assuming anything about the mapping from X to Y. So often in learning, in supervised learning, it's a convenient assumption to say, suppose that Y is very well predicted by some simple function. I'm not making that assumption here. The true outcomes could be arbitrarily complex functions of the inputs X.
I may not distribution from which X is generated.
You may, I won't need that assumption. I'm just going to assume that it covers the populations that I care about.
And that you can sample from that.
And that I have samples from that distribution.
So that the problem becomes trivial if you assume like linear separators or something like that?
That's a good question. Not necessarily. Okay, I guess it depends on what we mean. If the problem is, say, easy to pack learn, then we'll see that this is a solution to multi-calibration. So maybe it does trivialize. So really, I want to focus on the agnostic setting, where this map from X to Y could be very complex. Good. So let's return to this idea of miscalibration and calibration and be more precise about what we're talking about. Okay, I'm going to say that a predictor is calibrated if for every value that it spits out, when I condition on the inputs that I give that value to, its expectation is correct. Okay, so what does that mean? It means look at the individuals on which I say, you know, there's a 70% chance that they're going to have renal failure. Averaged over that subpopulation, defined by my prediction class, averaged over that level set, it should be the case that 70% of the time, their outcome is positive. Okay, so it's sort of an unbiasedness condition, but it takes it to the next level because we're conditioning on the level sets of my predictor. If you're gonna let people stare at that and ask a question if they want, this is like a very central notion to the rest of the talk. It took me a while to think about it the first time I saw it. But I think it's well captured by the fact that when my predictor says 70%, should actually mean it in the sense that it's averaged over the population, it's correct. Okay, and so we're going to take this to the next level and define a notion of fairness, a notion of group fairness that we call calibration across a protected attribute. Okay, so consider partitioning our input space X, the space of individuals, according to some attribute, say by race or by gender, age. You can imagine that there's a number of attributes you might consider protected. Partition the population according to one such attribute. A predictor is calibrated across this attribute if it is calibrated, even when I condition on membership in the protected or unprotected group.
So one calibrated is just, let's say, half the population is 1 and one is half is 0. You just like put 1/2 always.
You're 2 slides ahead of me, but yes, absolutely. Yeah, so this will be a very weak concept is what you're getting at. So
why is it B of A of X in the condition? So you condition only on the part of the population that is. Because P of A of X can be different.
I'm sorry, I'm not sure I understand. Could you repeat the question?
So actually, why isn't it the prediction instead of X, but of A of X?
So I'm allowing this predictor to depend on the individual's features. Okay, the features should be much more expressive than just this protected attribute. So the prediction is allowed to depend on all of those features. The only thing that I'm constraining, though, are sort of marginal expectations conditioned on the protected attribute. Yeah, good. So calibration is a strengthening of unbiasedness, right? Unbiased would say that just the expectation is equal to the true expectation. The expectation, say, of P is equal to the expectation of Y. But here, I'm no longer taking an expectation over P. I'm conditioning on the fact that the prediction is V, and saying that even amongst this level set where P is equal to V, it should be unbiased. Okay, so let me talk about this notion, and hopefully it will become even clearer as we go. So there's some hope that if we enforce calibration across these attributes, across a protected attribute, that it would move us from a situation where we had this attribute independent threshold on the predicted risk. We ended up with 2 different thresholds on the actual risk. The dream would be that somehow this group calibration, this attribute calibration, pushes us towards a situation where we have independent threshold on the actual risk. Okay, but let's look a little bit further into this calibration condition. Think about what notions satisfy calibration. Off the bat, hopefully it's clear that the optimal predictions, the statistically optimal predictions, satisfy calibration. Okay, so if somehow I could get my hands on these statistically optimal things, this thing that I'll refer to as P star of X is the true expectation conditioned on the individual's feature, like individual level probabilities, then I would be calibrated. This is sort of our goal. This is the thing that would be great if we could get. But as I said, like in this agnostic setting, we're making no assumptions about this thing. This thing could be arbitrarily complex. I don't know how to get that. But at least it satisfies calibration. What else satisfies calibration? Well, as was mentioned, there's a trivial predictor that satisfies calibration that just spits out the mean for everyone. Okay, so for every individual in some subpopulation or in the universe, I'm going to spit out I'm going to look at what's the expectation of the outcome overall. Just give that out as my prediction, this mu. So why does that satisfy? Well, consider this expectation when I condition now on the predictions equal to mu. Well, this conditioning no longer does anything because everyone got that prediction. So that's just equal to the expectation of y, which is equal to mu. So calibration is satisfied. Okay, this is calibrated, but by averaging over the distribution, we've removed any information in this prediction, right? The only information that this thing contains is about the population as a whole. Gives us no information about the individuals.
I guess it's still fair.
Well, let's think about it. Okay, so let's think about what the consequence of using such a predictor is. suppose that I required this calibration across attributes, but what if in one population, I had a very informative near optimal predictor, and in another population, I just gave out the average prediction, right? So I'm going to claim that this cartoon could be the consequence of a predictor that is calibrated across a protected attribute A by giving out optimal predictions in the blue population and these trivial predictions in the orange population. What's the consequence of that? Again, so despite being calibrated in A, you've captured none of the variation in the risk, right? In actuality, in this cartoon, I'm saying there's risky patients, there's unrisky patients. There's a huge variation in this orange population, and you're treating them all the same. So when I draw, again, a fixed threshold on the predicted risk, there's a chance that I overlook all of the orange population, right? So yet again, despite calibration across this attribute, I'm observing disparate treatment. I'm observing that there are high-risk orange patients who are not being selected and not being triaged appropriately under this prediction score. Okay, so I would argue that these predictions are not fair. They're not, despite the hope that calibration across an attribute would promote fairness, we're seeing that it's far insufficient. Good. So really, the concern here boils down to the fact that the prediction quality across this protected attribute, the prediction quality depends on the protected attribute, right? So when the quality of predictions depends on the protected attribute, it can result in disparate treatment in the downstream decisions. And in particular, we saw how calibration across this attribute A could still ignore any variation within groups defined by A. For instance, the high-risk patients with a certain attribute. Okay, so the question then is, how do we ensure that prediction quality is good across the population, particularly within groups that are considered protected? Okay, and this is going to motivate our idea of multi-calibration, which we think about very computational theoretically. So let me say what I mean by that. So the observation that we want to make is that actually we can draw inspiration from learning theory. Okay, learning theory has this idea of concepts. Concepts are just functions that map from inputs, and they're Boolean functions, that often identify interesting subpopulations. Okay, so what do I mean by that? Think of a Boolean function that we'll call C, mapping from X to 0, 1. And we can define a subpopulation of the universe, some subset of X that's defined through the characteristic function. That if C of X is 1, you'll be in this subpopulation. If C of X is 0, you're not in that subpopulation. Think about defining a subpopulation through some simple computational model. So for instance, like a conjunction, a decision tree, a half space, something that, some concept that you could potentially learn. Okay, and the idea will be to not just require calibration, not just require calibration across a fixed protected attribute, but instead try to enforce calibration across subpopulations, across a vast group of subpopulations. For instance, try to be calibrated on the group of Black women who live in Oakland and wear glasses, not simply on these attributes marginally. Okay, and really the idea is to enforce this not just on one intersectional population, but across every subgroup defined by some concept class C. Okay, so if we think about this concept class C as giving us some sort of computational bound, then really we're asking you to identify or to be calibrated on every computationally identifiable subgroup. Sorry, there's a question back here.
I
At some point, if you define this, way, would you be essentially asking to be as accurate as possible?
So the question is whether I'm asking, if I define enough groups, am I asking to be as accurate as possible? For instance, if I took my concepts to be like delta functions, right? If I took them to be identify individuals, absolutely, right? And so the hope then is to go from a situation where the question is sort of what is feasible, okay? If I define my subpopulations as individuals, this is probably not feasible for a statistical reason.
Or whatever is represented in the features, like features are themselves kind of taking individuals and grouping them.
Features are themselves defining groups. Yeah. So, but I want to not just define them by single features, but maybe by intersections of features, or maybe define groups by linear thresholds of features. So let me give you a definition. So I'm going to fix a concept class. Fix your favorite concept class. Decision trees of depth 5, or conjunctions of 3 literals, or linear threshold functions with bounded weights. Okay? Once we have this concept class fixed, I'm going to require you to achieve calibration for every subgroup identified by this class. Okay, formally, a predictor P tilde is C multi-calibrated if for every concept in my class, I appear calibrated, even when I condition on membership, when I condition on the fact that this concept is 1. Yep. So I'm going to require you to do this simultaneously across these populations, across these subpopulations, which might be very non-trivially intersecting.
That's still the definition of a conditional. Whatever sets I can identify, I need to be.
So I need your score function, this P tilde, to be a function of X. If X is a member of many, many different subpopulations, what function do you want to output? What prediction given X are you going to output? That is the multi-calibration question. So
The final sigma algebra, or the finest partition.
okay, yeah. So to another question, that's likely going to be individuals. So yes, P star, this statistically optimal predictor, is multi-calibrated. Great, yes. And the question is whether you can achieve this efficiently, because certainly you cannot achieve P star efficiently. Sorry, there was a question here. That refers, computationally identifiable refers to the fact that I'm assuming that this concept class, this concept is sort of computationally efficient. It's decision trees, it's linear threshold functions. It's not probably 100-layer neural networks. It's easy to calculate this C function. In some sense, it should be an explicit learnable function. Yep.
So are you kind of assuming that for some C, you're violated to get to identify?
Yeah, so great. We have to talk about how we achieve this notion, but and I promise I'll get to that, and that will be an element of identifiable. But for now, let's just think about the definition. Does the definition make sense? Yeah.
Is this a specialization of the attributes we talked about earlier with like some added conditions?
Yeah. So let me maybe just push forward. I think a lot of these questions are going to be answered in a few slides, but I promise I'll pause again if there's still confusion. So in fact, we're actually going to work with an approximate notion to address some of the concerns. There's no way we could actually achieve calibration on, say, individuals with perfect calibration, right? We need some sort of approximate notion if we want any hope of learning this from data. Okay, so we actually work with this approximate notion, but sort of for the sake of this talk, you can really think of, remember that there is some approximation, but don't worry too much about exactly how it's formalized. But throughout, we'll use this alpha as the approximation term. Okay, and so how does multi-calibration compare to calibration across a protected attribute? This is really sort of, I think, an important point. And so somehow, obviously, multi-calibration is quantitatively stronger, right? We're just throwing in more groups. So obviously, in your concept class is probably the protected attribute. So at least you're getting calibration across the protected attribute. But I want to make a point that multi-calibration is actually a qualitatively different notion. Qualitatively, it's trying to do something very different than this calibration that binds only at the level of protected attribute. Really, the point is that we want to require learning within not just the protected group and not just the majority group, but within any population that you can identify. Okay, and so here's sort of an observation that I put in sort of, it's stated very informally, but I can make this statement formal in a number of different ways. So if the true probabilities vary across the population in a way that can be modeled by some function in your class, that correlates somehow with some concept in your class, then a C multi-calibrated predictor has to model that variation as well. Okay, it has to pick up on it. So let's go back to our cartoon one more time. Think about what happens with C multi-calibration. So really the hope is that C will help you to identify different subgroups in your population that you cannot see, I don't think, in this projection, but trust me that I've drawn a box that represents C equals 1 around these points. And so so let's think about it. These predictions might be, we said that they were calibrated overall because maybe they're giving out the expectation in the entire orange group. But as soon as we split up this orange group and focus our attention on the upper half, then this low average prediction is no longer calibrated, right? So it forces us to split these up and give out higher predictions to those individuals. Okay, and now we might look and say, look, overall, these predictions aren't calibrated anymore because to be at this point, they were relying on these upper predictions to average them out. So we have to move those down. And then maybe there's yet another prediction or another concept in our class, the C prime, that didn't seem to have correlation with the function with the population originally, but now that we've split it up, forces us to make distinctions even further and refine even further, hopefully pushing us towards this attribute independent threshold on the actual risk. Okay, so that's the intuition behind multi-calibration. That's really the intuition behind why it's sort of a qualitatively different notion than calibration across a protected attribute.
So just to make sure I don't miss an intuition with, for example, here we would think of like some of the C's would be like the high-risk patients.
That's sort of our ideal setting is where the C can identify, say, high-risk and low-risk patients, not just overall, but even within subpopulations.
Kind of you bucket the outcomes.
Yeah, and so like imagine a scenario where, within a protected group, within a marginalized group, there is a predictor that does pretty well on that group. But because they've been marginalized, because maybe they are not represented well in the population overall, the predictor is not chosen. Even if that predictor is in our class now, we have to identify them. We can't overlook that variation. Yeah.
So isn't that precisely the setting where in some sense P is learnable?
So that's a great question. That's a great question. So the how learnable the P star is a great question. So our hope is that C at very least correlates with P star. And we'll see that it doesn't need to correlate so strongly for us to make really good progress. That if we have a bunch of C's that all partially correlate with the output, then we're actually doing pretty well. But yeah, there is a tension there. A different way to say that is that we're doing the best we can with given some computational and statistical resources. Okay, good. So that's most of what I want to say about the intuition behind the fairness properties of multi-calibration. These properties have been studied in a number of different works, including in terms of the underlying ranking of the predictions, in terms of error rate guarantees under post-processing. You can even think about getting calibrated in confidence intervals on predictions across groups and subgroups. So we can reference these works and go to them and look at different fairness properties. But really the outstanding question that everybody in the room should be asking is multi-calibration feasible? Like I presented this notion as this like amazing thing that gets you everything that you want, but requires you to reason about this huge number of groups that maybe identify individuals or require you to go to the bottom level of the sigma algebra. Like what's going on? How do we actually get this thing? And so the answer to whether it's feasible is a resounding yes. Okay, so in fact, there's a learning algorithm for learning a C multi-calibrated predictor that uses a bounded number of samples and uses a bounded number of calls to supervised learning procedure. Okay, so first off, let's talk about the sample complexity. The claim is that I only need basically VC dimension number of samples from this distribution that I assumed that I had access to. So the VC dimension of C is bounded by the logarithm of the cardinality. So one way to think about this is it says that from a polynomial size sample, I can protect and reason about exponentially many subpopulations. Okay, so good. That's what I want to say about the sample complexity. In terms of the learning complexity, in terms of the computational complexity, what we show is that you only need to make calls to this thing called a weak agnostic learner. So in theory, this thing is pretty hard to implement. There are hardness results for weak agnostic learning, but it is sort of the core backbone primitive of algorithms like boosting. Okay, it's the core supervised learning primitive. It's in fact easier than ERM. So what I'm saying is that learning a C multi-calibrated predictor reduces to the task of machine learning with respect to this class of C. Okay, so really both of these things in terms of the VC dimension and in terms of reducing to supervised learning really suggest that you should think about C as a learnable class of functions. Yeah.
Proceedings if the true data were generated by the C functions.
No. So okay, I'll show sort of how we use it, but a weak agnostic learner, you should think about it as a correlation problem. So I give you a set of arbitrary labels or arbitrarily labeled data, and you want to find me, does there even exist some C in your class that correlates even a little bit with the labels? Weak is for that. So very much it comes from like this boosting idea. Mm-hmm.
You didn't say anything about the class that you're learning, like what is the class that your predictor belongs to?
So I'll show you in a second. Yeah.
Is there some discussion about accuracy? Because we can have multi-calibration and
Yeah. So the whole second half of the talk, we'll talk about this. Yeah. So let me tell you briefly about the algorithm. The algorithm as sort of a pseudocode fits on this half slide. Okay. So what are we going to do? We're going to initialize the predictor completely arbitrarily. Give me some predictor. And then we're going to repeat the following iterative process. The first step, these first two lines, check the multi-calibration constraints. Okay, does there exist some C in my class on which the predictions are miscalibrated? Find me that C. Okay, if such a C exists, then update your predictor based on this violated C and based on the level set that it was violated on. Okay, and just repeat this over and over and over again until you terminate. Okay, and terminate when you can't find any more updates to make. So what does it mean that you can't find any more updates to make? Well, if you can't find a C on which you're miscalibrated, then it means you're calibrated over every C. So termination guarantees that I'm C multi-calibrated. That should be sort of obvious or immediate from this algorithm. The question then is, how many times do I have to run this, right? How do I know that this procedure will ever terminate?
What should I think of alpha as a constant, or?
Think of alpha as a small constant, 0.1% or.
Just as a, like, isn't like a lot of, I thought, when I read about fairness, often it's like that you don't have enough data about the group. And here it seems like if CX is then like not one enough, you will be trivially satisfying this and like by setting C.
That's right, that's right. So you're absolutely right. I'm going to need that these C's have some density in the distribution as well. Like that their image has some density. Yep. And that relates to sort of a whole issue of how we define approximation. But you should think of alpha as a small constant, 1%, 10%, whatever you can afford with your data, really. Okay, so but the point is that every time we make such an update, we can measure the progress we make according to some potential argument. And really, it's a standard potential argument. You can't run more than 1 over alpha squared times. Okay, so maybe that tells you how to set alpha as well. Okay, so the claim is that when this algorithm terminates, I return a multi-calibrated predictor. Here's where we use the weak learning. Look, so in fact, at every step of this iteration, requiring you to say, does there exist some C in your class on which you're miscalibrated? It turns out that I can reduce this search problem, this search over this class C, to a learning problem over this class C, right? I can concoct labels that I can then plug into a standard supervised learning routine and reduce this search problem to a learning task. Let me just answer the question about the class that this model comes from then. Really, this class of predictors is very similar to that which you would get out of boosting, right? So I'm building up my predictor P from additions, from linear combinations plus some conditioning, but of the underlying models from my class C. So the claim is that with not too many updates, with not too many additions of this form, I'm gonna, at the end of the day, build up a circuit that is only 1 over alpha squared copies of some function from my class C. Okay, so P tilde lives slightly outside of this class C, but only slightly. Okay, so the people who were paying especially close attention to this learning algorithm might have noticed this other proposition, that in fact, learning a multi-calibrated predictor actually reduces to the task of auditing for multi-calibration, right? So a lot of work and effort and interest in this area of fairness is about the idea of auditing predictors. Can I audit a predictor and tell you whether it satisfies your favorite notion of fairness? Well, the point is that the key subroutine in this HKR algorithm was whether or not you're multi-calibrated. If you're not, find me a witness. If you can witness the fact that I'm not multi-calibrated, then I can make progress. And I can use that auditing procedure to update and to make progress. So really, this can be viewed also as a post-processing procedure then. Hand me your favorite predictor that you've learned using whatever method you like, your most sophisticated methods, and then I'm just going to run a small number of iterations of this multi-calibration algorithm and spit out a model that is just a slight post-processing of your model, but also satisfies multi-calibration.
This is something, but let's say my predictor was a linear one, but the modified one may not be.
If your model was a linear model, then the post-process model might not be. That's correct. The post-process model will incorporate functions from my concept class C.
It might be like a collection.
It might be however many iterations I run, there will be that many copies of some circuit from my class C that builds up a larger prediction function. But very importantly, this complexity depends only on C. Okay, so the number of samples I need, the computational task I need, and the size of the circuit that I output eventually, it all depends only on C. Okay, it only depends on this complexity class C, has nothing to do with the complexity of the optimal predictor. Right, I'm going to assume that the optimal predictor, this Bayes optimal, could be arbitrarily complex. And yet, as long as C has bounded complexity, then I'm okay. And I'll get an efficient multi-calibration algorithm and predictor. Okay, so I mentioned briefly, but this idea of auditing comes up a lot in fairness. There's been a lot of different works now on this idea of multi-group fairness. In particular, I want to highlight this work of Kearns, Neal, Roth, and Wu, which was contemporary with the work on multi-calibration. They were looking into multi-group variants of these parity-based notions like statistical parity and equalized opportunity. There's also been a number of recent works by members of the audience and others on figuring out how to do this, this learning, this multi-group learning that I've been describing to you completely as an offline procedure to be able to do it in the online setting. So even though my focus today has been on learning in the offline setting, a lot of people have been working hard to make it a reality that you can do this even online. Okay, I'm going to pause there. Happy to go back in slides, but are there any questions at this point before I turn the page? Yeah, so question is about the variance of the estimator. I use different language to think about this. In sort of the TCS perspective, we often talk about the sample complexity required to guarantee validity of our estimates. So certainly in terms of the polynomial factors of these alphas and such, we do worse than, say, standard supervised learning. But in terms of the leading term, this VC dimension, we're doing the same as sort of standard learning. Okay, so there is a price to pay, especially if you care about very small subpopulations. But sort of morally, we're doing pretty well. And sort of at the end of the day, it becomes a practical challenge of how do you get the data that you need to audit? Because if you can audit, then we can learn. Another question?
Sorry, I asked so many questions, but like,
No.
yes, coming back to this, like, it seems like when you talk about the original example of fairness, you can impact the distribution by going out and getting more data about the impacted race in this case.
Yeah.
So, like, has that been like here? This was stabilized. I'm given a distribution. I do what I can.
Yep. It's a great question. It's a great question to say, hey, it's a separate question. I made an assumption up front that like I didn't need to do this, but absolutely, this is a big assumption. So there's a great question, both technical and practical, of like, I don't have enough data. I don't have representative data. How do I test that my data is not representative? And how do I go out and collect it? Great question.
Started off talking about fairness between using some special protected attributes like mixed vendor, and then you said, oh, calibration with respect to those protected attributes might not be sufficient. And then we said, oh, but multi-calibration, if we have like more subgroups, this actually aligns with like having better accuracy. So like, should I think of multi-calibration as just a way to get better accuracy? But like, should I think of like, should I still think of fairness with respect to like these original groups like race and gender, or now am I thinking of, oh, now we should also be fair with respect to all these main subgroups that we're adding?
It's a great question. So really the perspective here is that you're in a setting where if you had the optimal true probabilities, that your features are represented enough that the true probabilities give you a way to make a fair decision, whether that's by using a fixed threshold or by correcting and using different thresholds for different groups. But yeah, so this notion is very much aligned with accuracy, and we're going to talk about that in the next chapter. Okay, so I'm going to switch gears now and talk to you about optimal decision making, and talk to you about loss minimization, something that seemed to have nothing to do with multi-calibration. Okay, so loss minimization and agnostic learning is kind of the central problem in supervised learning theory. Agnostic learning asks you to find a hypothesis H with loss competitive with the best in some class C. Okay, so here I'm thinking of the loss as maybe arbitrary loss functions here just map decisions or actions, predictions, whatever you want to call them, and outcomes to some non-negative value. Okay, so here I'm thinking about hypotheses living in some decision space or mapping to some decision space that I'll call T. But you could think about it as the interval from 0 to 1. You could think about it as binary or over a fixed collection of actions. Okay, so hopefully loss minimization as a paradigm is familiar to many people. It's sort of the central paradigm of learning, supervised learning. Okay, note that in the first half of this talk, first 2/3 of the talk, multi-calibration made no reference to loss minimization. Right? I never talked about minimizing some loss. I just gave you a bunch of constraints. But intuitively, at least, we argued that multi-calibration somehow required learning across these different populations defined by C. So a very natural question then is to ask whether multi-calibration implies some loss minimization, and if so, for which losses? So to answer that question, I'm going to start off by saying it does imply loss minimization for the squared loss. Okay, so in particular, if p tilde is C alpha multi-calibrated, then its squared error on the outcomes Y is at least as small, or yeah, as every squared error in your class C. Okay, so how am I going to prove that? Fits on this slide if you believe the next two lines. I'm going to claim that multi-calibration actually implies these two weaker conditions. One is called multi-accuracy, one we call degree 2 calibration. Just going to have to trust me or do it in your head that it implies these things. And then the proof is a one-liner. Okay, so in particular, I'm writing out the squared error for any C in the class, subtracting off the squared error of p tilde. And again, you're going to have to trust me or verify quickly that I can express this as the following sum of the multi-accuracy error here in green, the degree 2 calibration error in purple, which I'm claiming are both close to 0, plus the squared distance between C and p tilde, which has to be non-negative because it's a squared distance. Okay, so what I'm showing is that the difference between these things has to be non-negative. So p tilde has to be a minimizer. In fact, you know, there's a stronger statement that you can make that somehow the suboptimality of C is related to its distance from P tilde. Okay, so the further you are from P tilde in squared error, the worse predictions you're giving. Okay, so that really gives us some sense that P tilde is learning a lot and doing well, but maybe it's just for the squared error. So here's a question that again might seem unrelated. When we do this agnostic learning, when we do loss minimization, a lot of effort goes into choosing our loss appropriately, right? In particular, the optimal hypothesis that we get at the end of the day very much depends on the loss that we've chosen. What about loss-independent agnostic learning? What would that mean? Is there any way to perform this agnostic learning without depending so much on the loss that you choose up front? I think when I first heard about this problem and when I've explained this problem to most people resoundingly say no. Like, obviously, your optimal hypothesis has to depend on the loss pretty intimately. But let's consider a setting where you can get optimal decisions for many different losses without knowing the loss up front. So suppose for some outcome, I know it's true generating parameter. Okay, so I'm thinking of a Bernoulli outcome, y sub p, that is sampled according to the Bernoulli distribution with parameter p. Okay, then I claim that for any loss function that you choose, there is an optimal decision rule, tau sub L, that takes in this probability p and spits out the optimal decision rule, right? It's just this minimization over this explicit expectation, which you know the distribution of. It's just saying that for a given loss, if you knew the true probability governing the outcome, you could minimize the loss. Okay, so an immediate corollary of this is that if I had the Bayes optimal predictions, this P star, these governing probabilities, then I could get an agnostic learner by composing this optimal decision rule with P star. So given an individual X, I'm going to run it through, learn the optimal prediction, and then post-process accordingly. So for any loss class, for any class of function C, tau sub L composed with P star is an agnostic learner, satisfies this guarantee. In fact, with epsilon 0. This follows just by averaging the fact on the last page that everybody believed. Okay, question then is, can we emulate this behavior efficiently? Right, P star is, we're arguing in this talk, is completely inaccessible, but maybe there's a way to emulate this behavior without learning P star. Just beating these tests defined by C. So do people believe that it's possible at this point? Yes, if I was talking about it, would it be impossible? In fact, okay, so this motivates a definition that these researchers Gopalan, Kalai, Reingold, Sharon, and Viter studied, which is the idea of an omni-predictor. Okay, so an omni-predictor is a single predictor that suggests optimal decisions for many different losses simultaneously. Okay, so in particular, we define an omni-predictor. It is for a concept class C and a class of loss functions now, a collection of loss functions. P tilde is an LC epsilon omni-predictor if after we post-process by tau sub L, it is an an agnostic learner. It gives the agnostic learner guarantee for every loss in our class of loss functions. Okay. So it's one prediction rule, one predictor that somehow suggests optimal decision rules for all of these losses.
Could you remind me what tau L was?
Yeah. So this is just, I'm using the exact same post-processing that I'm going to use on P star, the optimal, statistically optimal. Let me go back. So it's just this, imagine that I knew the true probability of the outcome. then it's the rule that chooses the optimal decision given that probability. So if I promise you that that y is sampled from Bernoulli 0.7. Now, given the loss that you care about, post-process to choose the best action, post-process 0.7, right? Just choose the best action given 0.7. Okay. Does that make sense? So it's just, you can think about it, imagine that T, the set of decisions is finite. Just go through each decision T, evaluate the expected loss, knowing that the distribution is Bernoulli 0.7, and choose the best action. That's the algorithm that implements Tau-sub-L.
Argument to your like squared loss was the actual predictor, like the probability.
Okay, yeah.
Was it the probability or was it the decision?
Well, so in this case, for the squared error, the decision space is actually 0, 1. So the post-processing, so this is a great example. Actually, tau sub L for L equals the squared error is just the identity function. This will be true for proper losses, proper scoring rules. It's for, I'm thinking about sort of arbitrary decision spaces, but it could be 0, 1, it could be discrete, it could be interval 0, 1. Okay, let me push ahead and just, the question is whether efficient omni-predictors exist, and the claim is, again, a resounding yes, because multi-calibrated predictors exist. Okay, so the claim, their main theorem is that if P tilde is C alpha multi-calibrated, then it is an LC O of alpha omni-predictor, where L is the class of Lipschitz convex loss functions. Okay, so what does this mean? It means that multi-calibration implicitly guarantees loss minimization for all convex losses. You have to do this post-processing, but you can treat the predictions that it spits out as if they were the true predictions, as if they were the true probabilities governing this outcome, and you get a loss minimizer. Okay, so I'm going to push ahead. Sorry, Wonky. Because I'm running out of time and I want to talk about the final chapter, which is on some pseudo-random version of learning. Okay, how did these proofs of omni-prediction go? They follow, surprisingly, a sort of pseudo-randomness argument. Okay, so here's the argument. First step, consider the Bayes optimal predictor, this P star that we've been talking about, and prove that that's an omni-predictor. Okay, prove that P star is an omni-predictor. Second, argue that the multi-calibrated predictor, P tilde, in some sense fools this proof. In some sense, that the proof can't distinguish between if you replace P star with P tilde. Okay, and so implicitly then, if the proof can't distinguish between P tilde and P star, then P tilde must also be an omni-predictor based on number 1. Okay, so in other words, according to these omni-prediction tests, P tilde is somehow indistinguishable from P star. Okay, so this feels like a notion of indistinguishability. And in some sense, it's motivating this perspective that P tilde looks like the optimal P star according to computational tests. Okay, so what would that mean? Let me give you another cartoon. So imagine that you're given an X, input X, a prediction on X, which we'll call P tilde of X, and some outcome Y, okay? And so I present this to you, and I promise you that Y is drawn from one of two worlds, okay? Either Y is drawn from nature. Y is drawn from the true underlying probability distribution on outcomes, this P star of X. The alternative is that Y is generated according to this modeled prediction. according to p tilde of x that I let you see. Okay, and the question is, can you distinguish between these two cases? Okay, I promise you that y is coming from either nature or it's being generated from the probability that I've spoon-fed you, I've handed to you. Can you distinguish between these two cases? And sort of this perspective of indistinguishability motivates a learning paradigm to try to learn a model whose outcomes cannot be distinguished from nature's outcomes. Okay. Yeah, so good. So there's a few things I need to tell you. First of all, I'm not going to just have you look at each individual triple. I'm going to actually require this to be, allow you to build up a class of algorithms. Okay, so we'll think about a distinguisher algorithm now as taking an input x, a prediction p tilde of x, and an outcome y. And the distinguisher algorithm's job is to guess whether the outcome y came from y star or came from y tilde. Okay, so I want you to build up an algorithm that does this as well as possible. And in particular, it needs to do it averaged over the distribution on x's. Okay, so this motivates the definition of outcome indistinguishability, which is a notion that we introduced with Dwork, Reingold, Rothblum, and Yona a few years back. Okay, so in this perspective, I'm going to fix a family of distinguisher algorithms, which I'll call A. And I want it to be the case that my outcomes, that my predictions are indistinguishable from the outcomes of nature according to every algorithm in this class in exactly the manner I described on the last page. Okay, so in particular, a predictor is A epsilon outcome indistinguishable if for every little algorithm in our class, the probability, now this is taken over x and the draw of the outcome, but the probability that the algorithm accepts, that it returns 1 when the outcomes are sampled from y star, should be basically the same as when the outcomes are sampled from p tilde. Yep. I'm not sure how it, so I'm going to, I don't think it has to do with whether p tilde has access to real randomness or pseudo-randomness. Okay, so I'm going to assume that y star is generated randomly from the true distribution and that y tilde is generated, again, truly randomly, but according to p tilde.
Here,
So
the distribution is over x as well. Or?
the distribution is over x as well, yes. Okay, so I think we started a few minutes late, but I'm wrapping up, I promise. This is a notion. It's a strong notion of indistinguishability in a learning framework. What's the upshot? Well, our main theorem in this paper is giving a characterization of multi-calibration through the lens of outcome indistinguishability. In particular, a predictor is C alpha multi-calibrated if and only if you can translate it into this particular class of distinguishers that yields, and your predictor is also outcome indistinguishable with respect to that class of distinguishers. Okay, so we show a tight computational equivalence between this idea of multi-calibration and this indistinguishability notion, outcome indistinguishability. So what it says is that, I think what I take away from this is it really suggests a new paradigm for learning. In particular, a new paradigm for learning in settings where you have new concerns that you care about. So everybody think of their favorite property of a supervised learning model, right? Maybe this property has to do with fairness. Maybe it has to do with robustness. Maybe it has to do with privacy. You name your property, okay? We'll call it pi. How are we going to learn pi? Well, I want you to think up some ideal model. Maybe it's the Bayes optimal, maybe it's not. And prove that that ideal model satisfies your property pi, with no concern about how you would learn this either statistically or computationally. Second is squint at your proof, and squint at it and devise from your proof a set of efficient distinguishers that if you somehow fooled these distinguishers, your proof would go through. Okay, so for those of you who are familiar, maybe this evokes something like the sum of squares proof system for you, right? Squint at your proof and make sure that if you fooled these distinguishers, then the proof would go through. And then once you have this class A, just learn an A outcome indistinguishable predictor. And you can do that because we said that outcome indistinguishability is equivalent to multi-calibration, which we said was learnable. Okay, so together, just by turning this crank very mechanically, you immediately get a learner satisfying property pi. And again, if this proof can't distinguish P tilde from P star, then P tilde has to satisfy your property. Okay, and so I don't have any time to talk about it, but one example, I think this paradigm can be used very broadly. One example of this paradigm, we recently put it together with Karen, Goldwasser, Kreuter, and Reingold in thinking about questions of statistical validity under distributional robustness and shift. Okay, you'll see this, great. Okay, I'm finishing. So in this tutorial, we talked about multi-group fairness. We talked about omni-prediction. We talked about, finally, outcome indistinguishability. Throughout, we saw that these notions were connected through this notion of multi-calibration. Okay, really, I think this is, these are 3 points on a triangle. There can be many more points. I think this is really the start of sort of a different paradigm for learning that is useful for fairness and useful for robustness, and hopefully is useful for your favorite application too. We conceived of this notion 5 years ago or so, and really then it was rooted in this perspective of multi-group fairness. And we've seen that it's had application far beyond fairness. And so I really think we're at the start and not the finish. So with that, I'll say thanks and take any questions. Yeah.
So I want to come back to the question about like this. One, I'm trying to think about the concrete application example where for group fairness, multiple calibration and so on makes sense. Because like what I'm thinking is that suppose that you have a group and the probability of each individual in the group of being labeled positive is increasing. Let's say it's a continuum, right? Then multi-calibration on its own would just tell you that the probability of selecting someone in the group is equal to the expectation, but it will not, I think it does not tell you that it will select the best ones, right? Or am I missing something?
I'm not sure I completely understand your question, but we do definitely think about how, so in this paper with Cynthia and Omer and Guy and Galeona, the first one in 2019, we study how multi-calibration can actually be characterized in terms of a ranking solution. And really it says that you don't transpose people according to the rank of their predictions. So that if your goal is ranking, or if your goal is selection rules with a fixed threshold, like you can make very formal statements about the fact that you don't overlook or you don't select the wrong group. If it's really a selection about who has the highest probability.
I'm not sure I understand the kind of discussion, because like multi-calibration with respect to some C gives some guarantees. It really depends on your selection of C.
That's right. And there were multiple questions alluding to this fact that there are very interesting and important questions about how your class C connects to the underlying distribution. If C doesn't identify useful structure in your distribution, then your host. Yeah, so really it's But the nice thing about it, right? The nice thing about it is that I can tune this C. I can think about C as a tunable parameter that given my data, given my computational power, what can I afford? And let's get the most that we can given our data and our computational power. And then if it's still insufficient, let's go out and collect more data.
Take other questions offline. Let's thank you again.
Thanks. Let me turn this off. So.